Hello, I'm Marta, and I'm a postdoc at the Seismology and Wave Physics group at ETH Zurich. I'm also part of the European Centre of Excellence CSCS, where I work with researchers from the Barcelona Supercomputing Center on developing a prototype of a workflow for seismic urgent computing. We're exploring the possibilities of using supercomputing to obtain fast shake maps right after an earthquake has happened, and I would like to introduce you to the prototype of our tool. So let's get started.
Urgent Computing Integrated Services for Earthquakes, UCIS4EQ depicted here, is a set of containerized microservices that each tackle a different task, with interactions between those tasks orchestrated by a workflow manager. The alert service queries databases in real time for information about new earthquakes and performs an analysis of the event. Should the event be candidate for an urgent simulation, the pre-processing step prepares simulation inputs. The jobs are then submitted to the HPC cluster to run wave propagation simulations with Salvus, a software suite by Mondiac, fully integrated in the workflow. Finally, the post-processing stage kicks in, generating a range of synthetic outputs. All this happens fully automatically and completes within minutes or hours, with the timing highly dependent on the frequency content of the simulations. The data access layer provides an interface to interact both with long-term data storage services and with short-term or intermediate information. Let's now move to the user portal, the UCIS4EQ front-end solution. The UCIS4EQ user portal provides an interface to monitor the status of the service and to examine the final results. In the Alerts tab here, you can explore all events that the Alert service has classified as urgent computing candidates. We pick up reports from a range of different agencies and need to unify that information later. In the User Event tab, the user can trigger the workflow for a specific set of parameters, adding an offline, non-urgent capability where parameters can be chosen manually. In the System Monitor tab, we can see the status of each event. We can follow the progression of all instances of the workflow, including both the automatic and user-defined events. The rejections that you see here are related to missing information for a given region, like, for example, the velocity model. In the Results tab, we will later see maps of outputs. To show you how the system works, we will now emulate the trigger of the magnitude 7 earthquake that happened on the 30th of October 2020 off the northern coast of the Samos Island. In other words, we send an alert that mimics the automatically generated alert. This launches a 1.5 Hz simulation, and we can see that it has been registered here. In the System Monitor, we can now follow the progression of all steps of the workflow. Once we enter the time loop of the simulation, we can also see that the wave field is propagating through the domain as expected. So now that the execution is finished, we can move to the Results tab. Once the images are loaded, we can select peak ground acceleration, peak ground velocity, spectral acceleration, areas intensity, or cumulative absolute velocity. Let's select PGA here. We can choose plots of each component or maxima over the components. Let's choose the maxima and the units here in %G. And we can see the respective plots for the maximum of all 3 components and the maximum of the 2 horizontal components. Now selecting the respective plots for each component, we've got here the east, north, and up components shown separately. This is just the first working version of our prototype, and additional ground motion parameters can easily be added in the post-processing stage. Finally, I'd like to mention that we have tested the workflow at scale, running 132 5 Hz simulations of the 30th of October 2020 Samos Izmir earthquake. One such simulation with Salvus took 3 hours and 25 minutes to compute on 2,160 CPUs, and running 66 such simulations simultaneously, we have occupied the entire Mare Nostrum 4 supercomputer. The same simulation takes 1 hour and 25 minutes on 90 GPUs. So 60 such simulations would occupy the entire Piz Daint supercomputer. First results of ground motion proxies for higher frequencies are promising, with the values on the same order of magnitude as we see in the recorded data, as opposed to the lower frequency runs, like the one launched for the purpose of this demo, where the values were significantly lower.
If you have some extra time to spare or would like to know more, you can find the link to the longer version of this video in the description below. And if you have any questions or comments, you can get in touch either with me or with one of my colleagues at the BSc. Thanks for watching.